Okay, we're at time, so I'm going to go ahead and get started. We have a lot to cover in a short period of time. But I do want to start with a little bit of a question. Who in the room has no idea about concepts, has not tried them at all? Okay, that's a pretty healthy chunk. Who is actually using C++20 and just kind of wants to get started with them? We got a handful. Very good. And who are already veterans? All right, well, you can leave now. No, I'm just kidding. Hopefully, I'm going to show even the veterans a few things in this talk, which might not be as obvious as you would think. So we're going to go pretty quickly. As I say, this is a large topic. We can't do all elements of concepts justice within this period of time. But I hope to show you a whole bunch of techniques and also talk a little bit about design. So we're going to do what I call climbing the ladder. We're going to start at the bottom, and we're going to also, just work our way up in complexity, in essence, with respect to concepts. Now, I have to say it's quite luck of the draw to be the person that is giving a concepts talk after the founder of C++ gives a keynote on concepts. If I had that in mind, I probably would have declined. But actually, I think you'll find this talk is focused at a very different level. Bjarne kind of went right into an intermediate advanced level of discussion about things, maybe without showing some of the principles and things that are behind concepts in the first place. So let me talk just a little bit about the state of concepts in general. Concepts is fully supported basically in all the major compilers at this point. My team has been using them in production code for the last 5 years, I guess, basically. They work beautifully. As a matter of fact, once you go down this road, you can never come back because the code is just so much clearer, so much cleaner, and so much obvious. And it gives you design concepts that you really didn't have. You could have done it if you're a fancy metaprogrammer, many of the things, but for this, you don't need to be a fancy metaprogrammer anymore. For this talk, you'll see there are Godbolt links for many of these things. So when you get the slide deck, you'll be able to follow those links and you'll be able to see the full examples. Of course, many of the examples are sort of cut down to size for discussion on slideware. All right, let's get to the basics of it. Why do we want concepts in the first place? And again, I think Bjarne did a very good job of expressing why. We really want to be able to write this generic code in a way that stays fast, has very good error messages, and makes the program as understandable as possible for our other fellow programmers, because really in the end, the program that we write is a lot for the human, probably more for the human than it is for the machine. Yes, we want the machine to be able to consume it and run it fast, but in a way that's really secondary when you think about it for a little while. And the last point I would make about this is that we want our interfaces to be more descriptive, and we want to be able to manage the dependencies between things. And I'll talk to you about how some of that can be done actually utilizing concepts. So what is a C++ concept in the first place? It's a Boolean predicate on types or values. I'm going to concentrate mostly on types in this talk. So everybody knows what a Boolean predicate is, right? It is something that evaluates to true or false. And these are examples of type requirements. We could say that a particular type has to have a certain shape in terms of its methods, its base classes or its subclasses. Those would be also part of the shape of a type, for example. And the one other thing I'll mention, and you'll note the asterisk on the semantics here, semantics have always been a part of concepts since the very beginning. I'm not redoing the history here, because Bjarne did a good job of doing that, but there's a long history back to the beginning of the STL. Those always express semantics. You'll see semantic requirements in the standard for things, and those semantics requirements are super important. Unfortunately, there is no such thing as a compiler that can evaluate those semantic requirements. So what we end up with is essentially syntactic, but that is very powerful in and of itself. So there's a number of things that come. So if you're a C++17 programmer, there's a number of new keywords. There's concept and requires. Those are two new keywords that you'll see, and we'll see lots of examples of that. You'll also see this pattern, and Bjarne kind of mentioned it, that he didn't like it, where you'll see a concept name. So that's a concept that's been defined, followed by auto. And that's used in a number of different places. But essentially what that's allowing you to do is, in place of a concrete type, you're basically able to substitute a concept, and then the concrete type is actually resolved when you compile with a specific type as a consumer. There's also new rules for function overloading. We're certainly not going to try and understand all the function overloading rules in this talk. I'm sure that could consume an entire hour, but the main thing to know is that concepts, we'll show you where concepts fit in the hierarchy. So one other important thing about concepts is they are composable. You can build more complicated concepts from simpler concepts. You have and or logic, conjunction, disjunction. And at the end of the day, what you're attempting to basically do is classify whether a type fits within the set or is out of the set. That's the Boolean predicate. So let's just drill in a little bit more on types versus concept. Everybody here knows what a type is, right? A type describes possibly a set of operations that can be performed. It has things like relationships, possibly to other classes, a dependent type, a base class, so forth. But in addition to that, a type has to be realizable at runtime. And this is one of the fundamental differences between concepts and types. Concepts don't live at runtime, they live entirely at compile time. And so when you have an actual type, you need a memory layout, you need a size for the compiler to be able to put that on the stack, on the heap, those things. In the case of built-in types, largely this seems implicit. If you have a structure or a class, of course, those are explicitly spelled out. So concept then really describes the shape of the type, how it can be used, the operations that can be performed on it, and as Bjarne mentioned yesterday, it can also describe relationships to other types. And that turns out to be super important for doing the kinds of things we want to do with concepts. So here's a very simple one, and I'm going to use this throughout. It's about the simplest possible concept that you can get. And for the moment anyway, I'm not going to describe to you all of the syntax here. The concept printable equal requires business. That's the requires expression. And what I'm just going to say, though, is semantically, or what this means is that for a type T to satisfy, that's usually the word we talk about when we talk about concepts, to satisfy this concept, it will have to have a method called print that takes an O stream, and that expression would have to evaluate to true for the type to satisfy this concept. So here I have a class, my type, and indeed this type satisfies this concept because it has a print method that takes an O stream, and that's it. So the very first thing from a practical point of view you can do in your code is now check whether or not a particular type matches a concept. So there are many very powerful uses of this idea where you want to enforce something maybe across a code base where you have many large numbers of domain types, and perhaps you have patterns for serialization or some other construct where you want to ensure, without even having to run a unit test, that in fact the type can satisfy those things. So If it doesn't satisfy that concept, that will fail to compile. You will know right away, and you will get an error message. So let me go back a little bit to the concepts of concepts. So as I've already sort of said, concepts are always a compile time item. There's no runtime footprint at all. You never see this in the linker. And this is part of what makes it very compatible with high performance code. This idea of the concept name auto, I'll show you in some examples in a couple minutes, is sort of a bridge between the idea of saying auto. You know, you've probably heard the rule almost always auto. Has anybody heard that rule? Yeah, not too many. Okay. Well, okay. We'll show you some examples. But one thing that means, right, this compile time presence means that for the evolvability of the program, and I think this was mentioned in the keynote questions a little bit, you basically have to recompile the program, all of the things that are dependent on a concept if it changes, right? So that's one aspect of using concepts. And of course, the core reason why we've been doing this really for decades, mostly with other kinds of hacks, instead of core language support, is we really wanted to constrain the types that go into a template. And that's really what we're talking about here. And we'll see a little bit more of that in a minute. Okay. Now I want to just focus, and actually probably the majority of the talk is here, on you as a user of code that is expressed in terms of concepts. I think that's one of those fundamental things that if you don't have a concept, again, an idea of what you can do, you might not be so clear just trying to, say, consume the C++ standard. All right, so what can we do with a concept, right? As we've kind of talked around, we can constrain an overload set. So if we have a function f, we can help constrain what function actually gets picked out of that set. We can initialize a variable. This might surprise some people using this concept auto pattern, and I'm going to show you examples in a second. We can use if const expr. Who uses if const expr here? A lot. Yeah, this is cool. So if const expr and requires clauses, as it turns out, even without concepts, is something that's possible. And I'll show you an example in a minute. You can do clever things, like you can say, I'm going to use a pointer, but I'm going to only allow this pointer to be of a type that models a concept. And I'll show you an example of that as well. We can partially specialize a template using a concept. That's not surprising. And then there's one other thing that comes along with the bundle here. It could subtly go by you if you're not expert in reading concepts. But the keyword auto has expanded its capability as we've gone along. And now a lot of template code does never contain the word template. And I will show you examples of exactly what I'm talking about. So what can't they do? You can't inherit from a concept. That's not an idea. So you can't create the same thing that you can create with a virtual base class using concepts. You can't constrain a concrete type using a requires clause. You can't allocate one. As I said before, the difference between a type and a concept is a type doesn't have any runtime presence. It doesn't have any size. And you also cannot apply a requires clause in concepts to virtual functions. So where can we write this concept auto thing I've been talking about? Well, we can write it in a whole number of places. Here's the list. I'll show you examples in a second. One place we can't write it as a member of a class, and we can't write it as a base class. That's sort of the same thing. Then the template parameter case and the aliasing cases for templates, you'll see that we don't actually need the word auto, which makes it even nicer. Okay, so let's look at some basic usage cases. We have our same exact concept from before. And here I'm going to define a function, f. And the function f takes a printable auto. Now, this code is a template. If that wasn't obvious to you, that is template code. But it will only allow something that models the, I'm using the word models as well. And there is a subtle distinction between satisfied and models. Those are two words that we use to express that a type actually fits into the set associated with a concept. Models is actually a stronger constraint because it means that the semantic requirements are also expressed, which again is not checkable. So sorry if I'm using those interchangeably if you are aware of those terms. So here's the other way, right? I'm going to initialize a variable called s, and it's printable. Anybody see a problem with this code? Yeah.
There's no type?
There's no type, yeah. Well, the guy behind you was going to answer, but you beat him to it. There is no type there. That actually will not compile, of course, because the compiler doesn't know what to do with a concept. It doesn't have a size, and it can't do anything with it. However, you can initialize the variable like this. You could have written a class on the right-hand side there, a constructor for a class on the right-hand side. But what it means is that, this init something function, if it ever changed its return value, it would still have to be a printable type, or this code would not compile. As long as it's a printable type, it will compile. It doesn't have to be the same type as it was before. So this is where that idea of an unconstrained auto is very different from the constrained version of this. And actually, let me go back and just, I think I have an example later, sorry, that demonstrates the dangers of using auto directly. Or actually, there are dangers in actually specifying the return value explicitly. Okay, so function parameters and return values. So here's a traditional template head, but you'll again notice that concept name printable there. So this is the case where we don't actually have to say printable auto. You can just put it in the template head. And that means that no type T, that doesn't satisfy printable will be allowed here. You'll get a compile error if you try to do that. Here's a return type that is flexible. It can be any printable. It doesn't have to be a specific type. So I have another function down here called print2. You'll notice it has no template head, right? This is the exact same function as the one above. They're equivalent ways to express the same thing. One is obviously a template. One, you have to understand the meanings of these autos to know that that's template code. I don't know, what do people think of that? Do people like the subtle version, or they want to spell out template? Okay. It's not as discoverable for juniors. Okay, that's an interesting comment. It's interesting in that it turns out my experience is that in the end, everybody learns that real quick. It's actually, I feel like it's better because it's just less, semantic overhead in your brain when you're looking at code. Okay, so these two are equivalent. All right, so let's talk a little bit about overload resolution, constraining function parameters. So I've already shown you a function that's constrained, and that constraint was printable. Now I'm going to write a new function called printline, and we're going to do this with first a template that is a traditional template. It's unconstrained, and again, I've shown you in the comments above how you would traditionally write this, but then the print line here, I've just said auto P. This is an unconstrained template. Any type, absolutely any type in the world will match that particular auto. And so what will happen, of course, is that if there is not a streaming operator for that type, it will fail to compile, probably with 100 pages of error message. Maybe not. This one's simple enough that it might not be so bad. So I have a type here also called myType. And if I try to do this here, what will happen is those first two lines will compile just fine, right? Because strings and integers have streaming operators. But this bottom one will not compile because there is no streaming operator for my type. So let's see what would happen if I wanted to have a print line, an overloaded print line that dealt with my type specifically. So I still have the template version at the top, which takes any type. And now I have another function here, an overload of the function, which takes my type specifically. So, and then does something else in this particular case to print it out. And what happens is that works exactly as you would expect it. Because the match of my type is more exact, it's more specific than the match of the template. So that overload succeeds, and the template overload does not succeed. The rules are wildly more complicated. They get wildly more interesting when you go into this, but that is very logical. It makes a lot of sense. It's an easy rule to remember. Okay. So I still have my printable here. Nothing has changed there. But now I'm going to add another concept here. And this is slightly differently shown. So output streamable. And this will come up in a little bit. Again, it's a very simple concept, only basically one requirement that you have a streaming operator. So let's take a little detour back to printable here and ask the question, what would happen if print were not public in this case? Remember that we've specified here in this line here that I can say v.print to it. Well, if print is not public, that will fail to compile. And so you will get a satisfaction error of that. So things like public, private, those things matter. On the other hand, you'll realize that not every aspect of v.print is specified, right? You'll notice that there's no constness or no except expressed in that concept. And that means that this is perfectly fine, that this is a const function and not specifically matching a non-const function. So there are a bunch of things like this that allow flexibility, but on the other hand, if you're trying to pin something down very, very carefully, then you have to do a little bit more work at it. Okay, so let's now create a constrained overload for the printline function. So we have our traditional template that we had before, and now here we have printable auto, which means that anything that is printable will essentially prefer to use the template function on line 7 here instead. Okay, so that's another example of the overloading case. And continuing on that same vein, let's see what happened here. So what happens here is we again get a compile error because this mytype2 in this case, which I think is actually not, it's not highlighting. So, oh, there it is. mytype2 doesn't meet any of the criteria for either the primary template, which is up at the top here. That's the primary template. And it doesn't also meet the constrained template for printable. So that's a compile error. And I think, okay, good. So let's talk a little bit about pointers and concepts. So the output of this program, you can see here, it's basically printing out a couple of things. And what am I doing here? I have const printable auto star, right? So, and then I new my type. So my type from before models the printable concept, so that works just fine. If I did mytype2 in that line 20 or 10, sorry, suddenly that would not compile and you would get an error, and we'll see one of those errors in a minute. The next line is the interesting one, I think. You might be surprised to learn that you can say const unique pointer, and then when you do make unique on the other side, it needs to match printable, needs to satisfy printable, or that line of code on line 12 will not compile. So it's a very interesting use that allows you to say, I don't want to just take any kind of pointer in the world. I want to be able to constrain that down to a particular set of pointer types. So here's an example of what happens when you try to do that initialization with something that doesn't model printable. You get a compiler error. So this whatever down here at the bottom is just an empty thing, which obviously doesn't model it. You can see what the error code looks like. To me, this is pretty straightforward, but then I've spent a lot more time looking at these kind of errors. But the errors are pretty clear that you cannot satisfy the particular, this type, whatever, does not satisfy those constraints. And that's maybe time for an aside on that. One of the promises of concepts is better errors. And after several years of experience in the field, I would say that there is at least one group of people that are disappointed. Disappointments are common in our language, I guess. But in this particular case, not all of the error messages are as clear and obvious as this particular case. We're dealing with some pretty simple examples here. However, my general experience with it is it's better than what we saw before by quite a lot. Okay. I mentioned earlier that if const expr was part of what you could actually use concepts for. And as I sort of offhandedly mentioned, you don't even actually need a concept here, because it turns out the requires clause is actually all you need. That's allowing you to do this Boolean evaluation directly in an if const expr. So if we take a look at this code here, another version of println, yet more sophisticated version of it, that does something that says, hey, if I've got a printable, satisfies the printable concept, well, then I'm going to do something, else I'm going to do something else, right? And so for those of you who do not know if const expr well, what happens at line 6 is if that concept is satisfied, the block of code that goes underneath the if const expr is the part that compiles into the function, and the else clause is thrown out. It doesn't even compile into the executable. So, so that's the first half of it. And in this case, printable is v.print, right? So that's how it actually works. And then in the else clause here, we're just trying the streaming operator. It would have been better to use that output streamable thing that I defined earlier, which maybe was what I was intending to do with that slide. So again, in this case, everything works. And depending on whether you're at line 19 or line 21, you get a different branch of the if const expr here. So also in this slide, I've noted that as usual, there's more than one way to do things. In this case, what I've left uncommented is the shorter form of this, but you can also wrap it in a requires, and you can wrap it in a requires with a complicated expression, right? Ors, ands, and other Boolean tests and values can be written directly there without any concept whatsoever. Okay. Right, so I think I basically just said all that. Yeah. Okay. This next little example I want to show you actually comes via Jason Turner, who, of course, loves to play with these things. But there is precedent in other places, like in the standard library, for doing this. And I'll show you another example, more complicated example later. So what we have here is a little wrapper class. I've kind of unhighlighted all the unimportant stuff. We have a constructor here. And then we have this, dereference operator. And you'll notice that right after its definition is the word requires again. And then we have is pointer v of t. So if you are a programmer that uses type traits, you will recognize is pointer t, which of course is a Boolean expression that is, from the old days, as it were. But the thing is, many, many concepts are actually defined in terms of type traits in the first place. There's also, in the standard library, which we'll go over some of the standard library concepts in a minute, there's several places where you'll see there's a type trait that will do what it is and a concept that will also do a similar kind of test. So you have an option of how to do that. There are some good reasons to use concepts that have to do with the way the rules are propagated, which we don't have time to go over in this particular talk, but usually the concept is probably better, but then again, it's all defined in terms of each other. It's all Boolean expressions. In one way, you should look at this and think that anytime I see a requires expression, a little constraint solver is running in the background of the compiler and coming up with the answer of whether or not this particular expression is true or false. But the effect here is that the operator star does not exist if is pointer v is false. And so this first set of code in line 13 to 15, where I use int star in the wrapper, works just fine because the t type is a pointer type. And so that function is available to call, or the dereference is available to call, and it works just fine. However, if I wrap a plain old integer and I try to call that same function, it will fail to compile. Okay, so this is the kind of thing that gets to the heart of design, right? Because a lot of design is about variation between things, right? It's like sometimes I want to have this variation and sometimes I don't want to have this variation. And concepts gives you a very powerful set of tools to actually express those variations. Okay. What if I wanted to say, have a vector that would be constrained? Can I really do it without rewriting all of vector? And it turns you can easily do this. You basically can use a template alias with a concept. So you're not going to say vector anymore. You're going to say vec of printable in this particular case. But what it means is that if I use a vec of printable, whatever type is in there, it doesn't say it's a specific type, but it's constrained by the fact that it has to be printable so that this code will actually compile correctly. So what if I try to put something in there that doesn't work? Then I get another error message, a compile message like this. And my recollection of this slide, it basically says, int isn't going to work here because, you don't have the thing that's required to satisfy printable of t. Okay. So that's, usability or usage of concepts without explaining how to write them, how to do any of that. I'm going to go through this next session at light speed. Largely, the slides are here for you as a little bit of a guide and a grouping and something that, to organize your thoughts about what is in the standard library. There are an amazing number of great concepts in the standard library that were agonized over in very difficult, it took a lot of time to get this right. And, as of the 4 or 5 years ago, there were people saying that, mere mortals can't even write concepts because, honestly, which of course it turns out to be completely and utterly false. But because the struggle over the standard library concepts was quite hard. So these are some groupings of them. Let's go through them. And I have to go back to type traits for 1 second and mention that type traits come into this whole thing because many of the standard library concepts are defined in terms of type traits. You might also want to do the same thing in many cases. Okay, so Here's a set of things related to numerics. Unfortunately, I think integral is the worst classification here. In my lightning talk tomorrow night, I'll explain why. Here's what they are, and the light description of what types actually match these things. Equality comparison. So you want to know if I can compare two things. Again, you might be removing a function from something if you can't compare the two types. And that's the bottom one. You'll notice a pattern here already that's starting, which is we get equality comparable T. So that's comparison against your same type, right? And T and U is I have a different type and I want to tell if I can actually compare that given type. Ordering. So this is another capability. You want to know if you can sort, do all sorts of comparisons and ordering. And then we get object relations. So we've said that several times that there are these two parameter concepts that can tell you something about whether the nature of two types. So same as is one that comes in a lot where you want to say, U and T are actually the same type. They have to be the same type or I'm not going to do something. Derived from, convertible to, assignable from. Those are all hopefully pretty obvious. And then there's a whole series of things about construction and initialization. And then we get down to some of my favorites, semi-regular and regular. Who's familiar with Sean Parent's talks on regularity? If your hand is not going up, you need to go search the web and watch talks about regularity, where it comes from. It comes from the original STL. And it's basically saying, this is a way that a type will be well behaved with all the normal things that you can expect. And we'll go into a little bit of an example here. Again, in our code, we frequently do this where we just have a static assert in the header that says, this type is regular. Because remember, to be regular, you have to have move, copy, and a whole series of functions. And we want to make sure that our types are regular so that they behave well in various circumstances. And this is a simple way to do that. Anybody see the problem here? Well, not enough people in the room knew what regularity is to know for sure. But this does not compile because this type, even though it has auto-generated constructors, move constructors, destructor, all that stuff's auto-generated by the compiler. You all knew that. But do you know all the rules for when they're generated and when they're not? I mean, there's a lot of rules to remember. So I don't ever trust myself on that even. But basically, it doesn't actually compile because regularity requires that you have to have equality comparison. And so when you look at the error, it basically tells you that. And basically, you have to add your operator equal and define it. In this case, we just need to tell the compiler, just give me the default one. That will work just fine. And now for a second, I want to talk about range concepts. So you may or may not be aware that concepts as a mechanism appeared at the same time as ranges. And part of that was that the feeling was basically that ranges were not going to really work well without having actual language concepts. And so it was also a great test of whether the language concepts would work. And I think that there's no question that this has been a very good success. So this print int function that you're seeing on the screen takes a standard ranges range, which is a concept from the ranges library that basically says, in essence, hey, you're a range if you have a begin, end, and you are like a sequence, basically. It's actually a pretty simple concept. So what does this enable us to do? Well, print ints works with every single thing on this slide: vector event, array event, span event, C array, etc. Oh yeah, iota view. Right, iota view is a generator function, essentially, that counts to the 1 minus the end of the range there. So every single one of these are the same input in the end, but they're all different types. If you had written print ints in terms of vector, of course, you couldn't reuse any of the code associated with this. It's a massive expansion in your ability to write generic code. I think this is like the simplest example of how it just changes the game completely. Now, I will admit there could have been more here. We could have actually written a more complicated concept that would also guarantee that the input was an integer type, but we didn't do that here yet. Okay, we're doing okay-ish on time. So reading and writing concepts. So you've already seen a bunch of requires expressions and clauses. As mentioned, Boolean expression, and you've noticed, hopefully, that right after a function declaration, you can say requires, and then some actual expression. The expression itself is the syntax that you're using to describe the Boolean constraints. There's a little bit more detail here in that there are different variations of it in terms of you can have a sequence. And on that second line, line 2 there, that's the one that you saw where we're actually passing external parameters into the constraint expression. And by the way, line 5 and 6 is like the simplest concept you can write. I mean, it's a Boolean, right? It tells you that it's always true. That actually is surprisingly sometimes handy. So here's another more expanded version of the print. So we've got a whole, let's see if I can make this pointer work. That'll be a miracle. No. Oh, there we go. So if you look over here on the right-hand side, we have the original thing we had. We have this second line, 7 here, which says, I have a free function somewhere in my translation unit called format, and I need to be able to call format with v. So this is constraining, or it's allowing, or it's saying, listen, this better evaluate to true, otherwise the concept will evaluate to false. Movable is a concept from the standard library that says, yeah, you can move this thing. And this last one here is saying that the T type itself has a dependent type declared within it called format, okay? So this is not really realistic, but this is to give you an idea of how powerful this is. There's a lot of different things that can be expressed in a constraint. The output streamable one I showed you briefly earlier is now enhanced down here on line 16, and you'll see std same as, which was one of those concepts we flew by. And that arrow syntax means that means the return type is constrained. It must be an std ostream, and that std same as evaluates that, oh yeah, that's actually an ostream. So that requires more of the return. These other ones up top, they don't specify what the return value is. It could be anything, okay? So the constraints expand or contract depending on how strict you want to make them. Okay, we've mentioned several times that you can compose constraints. So here's an example of a concept that has only requires clause. It doesn't have the other things, and it's got a bunch of Boolean expressions. Line 2 through 4 are exactly the same as line 7 through 9, except for we've used the or keyword there instead of bar. Everybody knows that or and and are keywords in C++, right? Do people actually use them in if clauses? Okay, there's a couple. I like to use the and or expressions in concepts because to me, it just reminds me that I'm in a context constraint context. We don't have probably hardly any code at all that uses and or in actual traditional if statements. So the bottom one is an and, the top one is an or, and I think it's pretty obvious what we're doing in the compositions there. If you look at the standard library constraints, they're a lot more complicated. you'll see, just to get down to regular, it's probably a dozen or more different kinds of constraints in total. This is just some more examples of doing the same thing. And maybe I forgot to mention, did I go by that too quickly? No, maybe that's coming up. Anyway, this is just some more examples of similar sorts of things. You'll notice the bottom one here at line 12, we've sort of lifted the movable that is on line 5 out, and it's into, the first part, and then there's the requires expression that's at the bottom that contains the other two. They're basically the same thing. I'm going to skip over this one and this one for time. So I've been talking already about ranges and concepts a little bit, and I want to just show you a real-world concept definition that's a little more complicated to give you a flavor of how fast this gets into something that's a little more complicated. Now you'll notice here where we have ranges filter view, which evaluates the lambda there. When and in the for loop here, as you iterate over it, right, you're only going to get the even values, right? That's pretty straightforward. Everybody knows how to read that code. There's no template parameters, no concepts, there's no presence of anything, right? It looks just totally like normal code. This is what the template for filter view actually looks like. So there's a few complications. So that first thing, input range, V, that is also a concept, right? We've been seeing those concepts written in the template heads, and that means that the filter view must have at least an input range. There's an indirect unary predicate, iterator T, whatever, right? Well, that's saying that I've got something that's callable, and the lambda fits that particular description. And then we see more requirements pop in here. Requirements, view V and is object V. These are additional requirements, additional standard concepts that have to be satisfied. And then you'll notice, right? So remember, filter view is a type now, right? It's not a concept, but it's using a bunch of concepts here to say, hey, I need to have an input ultimately that looks like this. And then you'll notice this other thing. It inherits, right, from another type, this view interface type. And it passes itself in as it. Everybody in the room knows what that is, right? CRTP, the curiously recurring template pattern, right? But what's interesting about this is that that's an association, obviously, with another type, and that type here is also a constraint type. So to ultimately, instantiate the filter view type itself, it's constrained not only on the types that are the types that are going into the interface are constrained not only on the primary template, but also its base class template, okay? So view interface is actually a very interesting thing. Here's another example, like the pointer V case, where we now start to subtract a particular part of the interface by using concept constraints in view interface. So view interface is a base class, but any view that inherits from view interface, which is a lot of the views, by the way, in ranges library, can either have this, braces operator or not. And that is constrained on the fact that it must be a random access range, which makes all the sense in the world, right? If you've just got a plain input range, this will not work. So this is a little bit more complicated. If you start looking into C++26 ranges parallel algorithms, your head will explode. You will not be able to expand the constraint set in your head. I've sat and read a lot of these, and I can tell you I can't expand it. There's only 2 people on the planet that I'm aware of that can actually expand it in their head, and they make mistakes. So at a certain point, you actually need that constraint solver compiler to actually tell you how the constraints all expand, which means that it does get difficult to write some of the complicated cases, but then there are a lot of patterns that you see over and over again when you start dealing with things like ranges. So, okay, I'm going to quickly talk about designing with concepts. We got 10 minutes left. I was hoping to leave a little bit of time for questions. So, designing. What is design anyway? So, there's another version of this talk that took 3 hours, okay? And this section of the talk took an hour by itself. You're getting the TLDR version, okay? And there's a reference to the other talk. If you want to go see the second half of that talk, I go into a ton more detail about what this stuff means. But we have all these different paradigms, and what does it even mean? And the real thing here is, at the end of the day, most of the design comes back to divide and conquer of some form, right? Like, you need to take a big program, split it up into smaller bits, and those parts will then have to interact by necessity, right? But those smaller bits can be reasoned about, they can be tested about in a simpler form, and we can get their correctness right. And it, allows you to separate out the pieces that don't really logically belong together. Well, then we get into a divided program, and we've created a bunch of dependencies. And what that typically means is design paradigms appear to help you deal with the fact that you're dividing up the program in certain ways. Okay? And that's what's on this slide is what I just said. So, concepts and dependencies. What can concepts do with dependency for us? Well, one thing is that we can move a dependency between specific types into an abstraction that is a concept, and then we can depend on that concept instead of the specific types. I've basically already shown you examples of how that is done. Does that solve all the problems? Well, of course, as soon as you've done that, you've moved the dependency to a different place. You've moved it to a concept, as mentioned. And that means that it will have to be reevaluated at compile time if, in fact, you change the concept. Now, I think this is basically the question that came up in Bjarne's talk, is, hey, if I change the concept, doesn't that mean like you're going to break people's code? And the answer is possibly. It depends. But the main thing here is you're going to have to recompile. So you know that. That isn't necessarily the case if, in fact, you're directly dependent on a specific type. Even if that type changes, you might not have to recompile, especially if it's just an implementation change. So, you can either get the case where the type evolves and no longer matches the concept. That would be one possible thing that could happen. Or the concept can evolve and you have to recompile and see what fails. Now, my contention about this is that that's exactly what you want. If you change a concept or you need to update a concept to make it tighter, then you want the stuff that doesn't match that concept to not compile anymore, so you can go find it. It's also possible you're loosening the constraints and making them easier to satisfy to allow other types that would not previously compile to do it. So it's not a binary option in this case. It depends on what direction the change is made and what effect it's actually going to have. Okay. So let's talk about code readability. This is a slide I alluded to earlier. So line 1 is, unconstrained auto. The return type is whatever some function is. If some function changes, it'll change to whatever that return type is and continue to compile. Now, whether stuff downstream of it will continue to work is another question. On the second line, we've constrained it to be exactly an integer. What could go wrong? Any thoughts? Well, sorry?
Be a long or something?
Bingo. As soon as I change some function to be a long return, this will still compile and it won't work right. That's brittle. So there's a good argument that maybe having the exact type there isn't always right. Now, maybe they're under certain compiler options, you might see a warning, but I don't know. That's for my lightning talk tomorrow too. Time duration here in this case is a concept which I didn't define in the talk. Only in the longer version of the talk did I define this particular thing. But it's interesting, right? Like, because that tells you something concrete. Like, I can go to the definition of the concept and say, what's a time duration? What shape does it have? And if some function now returns something that doesn't match that shape, it won't compile. I think it's actually very interesting balance between the almost always auto and a constrained auto, essentially. And I think it's a good practice, potentially. Okay. So I think I said all of that in words, and I'm going to bring this slide back up because the title is Breaking the Grip of the Type Dependencies, right? So it's always one-off in computer science, right? Like there's just one more level of abstraction and the problem is solved. And in this case, it actually is. And you're doing it with zero loss of efficiency. All of this stuff will compile down to the metal just as good as putting the specific type in there because the compiler will resolve the specific types at compile time. Okay. So, final thoughts. Yeah, it's powerful. Once you go there, you can never come back. Largely what I found with my team, some of whom are former C programmers, working in a world of C++ 26 now, is that they adapt to this extremely easily. There's no friction or overhead. I find them writing concepts to constrain templates that we have in various places. So the idea that no one that's a mere mortal can do it is just completely incorrect in my experience. Don't get me wrong, I have a very good team, but it's not crazy hard to learn. It's integrated into many, many aspects of the standard library now. I encourage you to use ranges. Don't listen to the stuff about ranges being bad. Remember, half the ranges library is actually just algorithms that are constrained by concepts to give you better error messages. You don't have to use a view to use ranges. Use algorithms that are constrained. They're better, and they will give you better error messages if you violate it. Okay, that's all I have. I've got 3 minutes or so for questions.
So is there any use for enable if?
You largely don't need it anymore. That's one of the benefits. Yeah, exactly. So, yeah, and actually, just to expound on that a little bit, right? So if you look at the standard library specification, you'll find a clause on function definitions called constraints, and that clause is usually a set of concept requirements, effectively that define that, hey, this thing's going to spine out if it doesn't meet these constraints. Other questions? Apparently I did a good job. There's no question. Oh, just a second.
Can you go back to that slide where the bottom requirement was checking the OStream ref was being returned?
The OStream. Oh, too far. Let's see.
Like you had squiggly brackets and then an arrow pointing to, I think, a concept check, but I couldn't tell.
Let's see here. You didn't happen to note what slide that was, perhaps? It was pretty late? Okay. Well, I didn't see it yet here. Sorry, this was the one with the pointer, or?
No, I was checking you were using the OStream, that the print would return the OStream ref.
There's a dereference missing.
Yes, that was the pointer, I think.
Oh, I'm sorry. If
it's
it's
okay.
taking too long, we can drop it.
It's fine. Okay, let's go to the next question. I'll see if I can find it while we're doing that.
So more of a comment. At the start, you had this that the two things are equivalent, that I can say template type name of something, and then I can just say the concept auto. Mm-hmm. There's one small difference. If you need to have something about the type T you had in the first place, then you can do this quite easily. If you just use concept auto, then you have basically using T declaration type and then have to remove the constant and reference and everything else. So that's then a little bit more verbose.
Yes.
So there's a small difference.
There are small differences, yes. Sorry, was this the slide you were talking about? No, not this one. Okay. All right, did we have any other questions? I think we're technically out of time, but come up and we'll find it. and I'll answer your question. Yeah, we got one more question.
Right. Is there any tooling or like possibly compiler features that would, let's say I write a function that takes a parameter and it's like some concept auto and then the parameter name. And then inside this function, I then use some feature of this type that's not actually declared in the concept. So basically I haven't clearly communicated in the signature what I want from the type. Is there anything that could like catch me like doing the wrong thing in that sense?
Well, the compiler will catch you more than likely, because if you ever pass a type, the problem is it's not going to catch you if you don't pass a type that doesn't have that function, right? So, so that's a whole part of the other talk where I talk about some things about, well, how do you get to a good concept design in the first place? Which is, I think in my experience, if you're doing something that's not sort of mildly trivial, I'll call it, just composing several other concepts together, for example, if you're from first principles trying to build one, it can take some time to do well. And in part, that's because of exactly what you're talking about, right? Like you need to understand what the function itself is going to do and what all the downstream functions on that particular type are going to require from that type to really bring it all the way up to that concept and be able to say, oh yeah, I've actually covered all the ground that this thing is going to do. Now, there's another thing here though that impacts, which is you might decide that the downstream functions that are being called on that type maybe aren't the set you want. You might want to redesign some of those downstream functions. So it becomes a very iterative process when you start trying to specify them. Yeah.
Thank you.
Yep. Hey, Chris.
On the question for tooling, people should check out CPP Insights by Andreas Fertig. It will expand out all the stuff as it's compiling and tell you what is being compiled and why.
That's a good point. I haven't tried it with concepts, but that probably is very
There's a direct link from it in Godbolt. If you're trying something in Godbolt, you don't know why it's working, hit the link and it will bring it up.
Right.
And you can test it right then.
All right. All right. Thank you, everybody.